In this lesson, we're going to begin looking at how to perform translations on the quadratic family of functions and the other parent graphs. In this lesson, we're going to focus on the quadratic function, the absolute value function, the square root function, and the rational function. So to start this, why don't you go ahead and complete the warm-up, pause the video, and unpause it when you're done, and we will go over it. So the warm-up asks you to describe in words what each of these translations on these functions is doing. So if we look at this first one, this is written in the form, in point slope form, in the way where it has both of these, both are lying. So remember we said if it's written like this, both variables are lying to you. So this is going to go down 3 and right 2. This one, y equals f of x plus 5 minus 2, because this minus 2 is not with the y, it does not lie. So with y lies, not with y does not lie. So in this case, the x, again, is always lying, so we're going to go left 5, but we are going to go down 2 to translate this function. Again, y equals f of x plus 4. This 4 is not with y, so it does not lie. So we are doing nothing. This is only x. It's not going left or right, but it is going up 4. And then finally, we have y minus 9. The minus 9 is with the y, so it lies. So it's going to go up 9. And then x minus 3 always lies, so it's going to go to the right 3. And what we're going to do today is we're going to use this information that we learned about translations in the previous lesson to start doing this with actual equations. So again, when we change the size or position of a figure or a graph, it is called a transformation. The graph that we're going to start with today is y equals x squared. And so in order to talk about this, we do need to remember a few things about y equals x squared. That is called the quadratic function. It is going to create a parabola, and parabolas always have a line of symmetry that passes through the parabola's vertex. And one thing that you'll notice is when we start talking about the equation y equals the absolute value of x, it also has a line of symmetry that passes through its vertex. So the parabola and the absolute value function, or the quadratic function and the absolute value function, share a lot in common. So a little bit about the quadratic function. The parent function is y equals x squared. If you were to create a table of values for y equals x squared, you would have something that looks like this. And what you'll notice is that the vertex is 0, 0, so it is in the middle, and the numbers repeat themselves on either side of this. And so again, knowing that your vertex is 0, 0 is going to be important for you being able to figure out where the new function is going to be located. So what we'll do is, and again, everything that we're going to see in this investigation can be applied to the other three functions that I've mentioned at the beginning of the video. So in this first step, what we want to do is come up with equations that represent the red function. We see that the original function, y equals x squared, is the black, and then our red function has been moved somehow across the coordinate plane. So if we look at this in relation to the black graph, the red function has been moved down 4 units. So we've gone down 4 units. And so if we were going to write an equation that represents this, you might see something that looks like y equals x squared minus 4. That is written so that it does not lie. You also could see y plus 4 equals x squared. Again, both of these are representative of the red graph moving down 4 units. Either one is correct. I would recommend that you choose one to use and be consistent throughout your work. In this second graph over here, we can see that the red function, the red quadratic graph, has been moved to the right 2. And so if we think about what that would look like, we'd have y equals f of x minus 2. But because we're using the quadratic function, that f is kind of a placeholder. So we have y equals x minus 2 squared. Again, what's written in there with the x is always lying, so since we're moving to the right 2, it's going to be x minus 2. Looking at this next graph, we have this function that has moved 2 units to the left and 2 units up. So we moved up 2 and left 2. And so if we're going to write an equation here, we might have something that looks like y minus 2 equals x plus 2 squared. In this form, both of the variables are lying, so we have that. Or you could write it as y equals x plus 2 squared plus 2. So why don't you go ahead and try B, D, and F, pause the video, and then unpause it when you're ready to check your answers. So for B, it has moved up 1 unit, so we'd have something along the lines of y minus 1 equals x squared, or y equals x squared plus 1. For C, we'd have something that says y equals x plus 4 squared, because it has moved 4 units to the left. And finally, with F, we would have something that says y plus 2, because it moved down 2, equals x 4 minus 4 squared. Again, how am I checking that? I start with my vertex on my parent function. I move over 4 to the right, down 2. Or I could write y equals x minus 4 squared minus 2. So again, this is how we're going to come up with these equations. You pick a point when you're dealing with your quadratic function or absolute value function. You're typically going to want to start with your vertex and see where the new vertex is going to be. So in general, as we look at these equations that we're going to be working with, your quadratic function is going to be written like this: y equals x minus h squared plus k, or y minus k equals x minus h. And this one on the bottom, they both lie, and on the top, just the x lies. The absolute value function is the exact same, except instead of having a squared, because it's not the square quadratic term, it is the absolute value function, we have y equals x minus h plus k, y minus k equals the absolute value of x minus h. Again, here both lie, up here just x minus h lies. The square root function, we replace the absolute value with the square root, so it's going to be y equals the absolute or square root of x minus h plus k, and y minus k equals the square root of x minus h. Again, down here, both variables are lying to you. Up here, just the x minus h is lying to you. And finally, you have the rational equation, rational function. It's going to be 1 over x minus h plus k, or y minus k equals 1 over x minus h. And again, down here, both are lying to you. Up here, just the x is lying to you. So what we're going to do is we're going to take a look at a real-world example here and see how this can be used in a real-world example. So in this example, it says the graph shows a portion of a parabola. It represents a diver's position, horizontal and vertical distance from the edge of a pool as he dives from a 5-foot long board 25 feet above the water. It asks us to identify points on the graph that represent when the diver leaves the board, when he reaches his maximum height, and when he enters the water. So when the diver leaves the board, that'd be right here, where he jumps off the board. He reaches his maximum height right here. So right here, that point is 525. He's 5 feet. He's out on the 5-foot long board, 25 feet in the air. He then reaches his maximum height, which appears to be at about 7.5 seconds at 30 feet. And then he hits the ground or hits the water somewhere right there. We'll call that at he's 14 feet from the board, or 14 feet out, and he hit the water, so it's 0 feet in the air. So now it says sketch a graph of the diver's position if he dives from a 10-foot long board 10 feet above the water. So if we did that, what we might do is, let's see if I can just sort of highlight this or make my own little parabola. There we go. So right there. And so if we think about what this means, it means that his starting point would be at 10 feet out, 10 feet over the water, which would be somewhere right about there. So at 10 feet out, 10 feet up in the air, he leaves the board. It then says, so there's our sketched graph. And so you can see right here, we have our max height, and then we hit the water out here. It says, in this scenario described in parts B, what is the diver's position when he reaches his maximum height? Okay, so in the scenario described above, what is the diver's position when he reaches his maximum height? That would be, his maximum height would be right about there. So if we think about this, what happened here was this point was shifted, translated, down 15, and then over 5. Okay, so we shifted it right 5 units and then down 15 units. And so if we think about our mapping notation, what we're doing to each x value is we are taking xy and we're moving it to x plus 5 and y minus 15. And so if we want to figure out what his new position is when he reaches his maximum height, or what is the diver's position when he reaches his maximum height, what we would do is we'd say, okay, well, his new position would be 5 plus 5, so, or it would be, we want a maximum height, 7.5, so he'd have 7.5 plus 5, that'd be 12.5, so he's going to be 12.5 feet out from the board when he reaches his height. And then we're going to go down 15, then he's going to be at 15 feet above the water. So on this new board, he's going to be 12.5 feet out from the edge of the wall, or edge of the pool, and 15 feet above the water when he reaches his maximum height. So 12.5 to 15. And again, we used our translation, our mapping notation, in order to figure out what our new x and y values would be for our maximum point. So we can take this and we can extend this to any type of function that we want. Again, we can extend this to square root functions, absolute value functions, and rational functions. So what we're going to do is we're going to take a look at 3 examples here where we have to figure out what this information is for each of these graphs. We want to figure out the parent function, the transformation in words, the mapping rule, the equation, and the domain and range. So the first one that we're going to look at is letter I. We need to be able to recognize what type of function this is. So this is a square root function. We know that the parent graph of this function is y equals the square root x. And so what we need to know, and again, I've been telling us that we need to make sure we know what these graphs look like. Our parent function looks like this. You start at 0, 0 because the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. And so our function looks something like that. And so our transformations in words, so what happened to this purple graph to make this red graph is we moved down 3 and left 1. So left 1 and down 3. That would mean that our mapping rule, which again does not lie, so our mapping rule is going to describe to us how we get our x and y values for the new graph. We'd take our parent function and we'd map it to, we would go left 1, we'd subtract 1 from our x values, and to go down 3, we'd subtract 3 from our y values. So our mapping rule would look like that. Again, what that tells us is with our x value, so here is 0, 0, we would subtract 1, that would take us to -1, and subtract 3, that would take us down to -3, which gives us our new point, -1, -3. And our equation would be either y plus 3 equals the square root of x plus 1, or y equals the square root of x plus 1 minus 3. And if we're looking at our graph here, we can see that our domain would be bracket -1 to infinity, and our range would be bracket -3 to infinity. In our parent function, for our parent function for the second graph, it is the absolute value function, which is y equals the absolute value of x. And we should know, again, what this graph looks like for its parent function. The absolute value is 0, 0. Absolute value of 1 is 1. And so we have a V-shaped graph that looks like this. And so we can see, if we look at our vertex for that graph, where it has moved to, we went up 1, 2, 3, 4, over 2. So we went right 2, up 4. So our mapping rule, again, which does not lie, would be x, y maps to x plus 2, y plus 4, which would lead us to having an equation of either y minus 4 equals the absolute value of x minus 2, or y equals the absolute value of x minus 2 plus 4. And again, this would give us a domain of -infinity to infinity and a range of +4 bracket to infinity. In our last graph, this is a rational function. The parent function is the rational function. It's going to be y equals 1 over x. So our transformation in words, how do we figure this out? Remember from our parent graph activity, we learned that there is a vertical asymptote right here at y equals 0 and x equals 0, so on the x and y axis. If we look at this, the easiest way to figure out what transformation has occurred is to take these two asymptotes and shift them until they line up with the graph. So if we look at that, we have moved our point 0, 0, where the asymptotes intersected, to right there, left 3, up 2. So the graph has moved left 3 and up 2, which gives us a mapping rule, which again does not lie, of x minus 3, y plus 2. And so our equation would be y minus 2 equals 1 over x plus 3, or y equals 1 over x plus 3 plus 2. And so our domain and range here are a little different. Our domain would be -infinity to -3, union -3 to infinity, and our range would be -infinity to 2, union 2 to infinity. So again, as you can see, the idea of these translations, finding out where they moved and finding out the mapping rule in the equation, that general idea does not change. The only thing that changes is which parent function shell you're using. So as you work on your homework, you'll get some more practice with that. The parabola y equals x squared is shifted to have a vertex of -2, 4. So if our function y equals x squared, we know that the vertex for that is equal to 0, 0. So if the new vertex has moved and shifted to -2, 4, what we have done is we have moved left 2 and up 4 units. So the equation for this would be y minus 4 equals x plus 2 squared, or y equals x plus 2 squared plus 4. Again, because we know that the vertex was 0, 0 and it shifted to -2, 4. Number 2 says, where is the vertex of the parabola represented by y equals x plus 0 plus 4? Again, we have learned that this value and this value represent our vertex of a parabola. So the vertex here would be 0, 4. It's +4 because that is not with y, so it does not lie. Letter number 3 says, describe the location of the function y equals f of x minus 3 plus 4 relative to y equals f of x. Well, x minus 3, x always lies, so we're moving right 3 units. Since that plus 4 is not with y, it does not lie, so that's going to move up 4. Number 4 asks us to determine the domain and range of each of the following child functions. So if we think about this, we'll do this in general. We know that this is a quadratic function, and so we know that the parent function typically looks like this, y equals x squared, but this is telling us that this graph is moving left 2 and down 3. And so if we take this little graph that we have and move left 1, 2, down 3, that tells us that we have a new vertex of -2, -3. So our domain is still going to be -infinity to infinity because that never changes for quadratic functions, and our range is going to be bracket -3 to infinity. Again, when you're doing this, you're trying to use what you know about the parent function and how it looks and what has happened with the translations. With this function, this is a square root function. We know it starts at 0, 0 and looks something like this. And then if we look at the translations, it has moved right 1 and up 2. So if we take our graph and move this right 1, so right 1 and up 2, we have our new point right there, which is 1, 2. And so if we look at our new domain and range, our domain is going to be bracket 1 to infinity, and our range would be bracket 2 to infinity. If you look at the function y equals the absolute value of x minus 4, again, this is the absolute value function, so it looks something like this. Let's do that a little bit better. So, so there's our function. And then what has happened here, nothing has moved left or right, but we're moving down 4. So if we're moving down 4, what's happening is this is moving down 4 to about there. And so we have this new function right there that is at 0, -4. So the new domain would be -infinity to infinity. That's always the domain for absolute value functions. And then you have bracket -4 to infinity. And then in letter D, you have 1 over x plus 3 plus 5. So again, this function is looking something like this. The important thing to remember is that the asymptotes are on the x and y axis. But if you look at this, this has moved left 3 and up 5. So instead of having a vertical asymptote that is on the x-axis, it is going to move left 3. So 1, 2, 3. So we'll have a vertical asymptote right there. And then up 5, instead of being on the y or x-axis, it's going to be 1, 2, 3, 4, 5. So it'll be up here. And so our graph will look something like that. And so if we take that, our domain would be -infinity to -3, union -3 to infinity. And our range would be -infinity to 5, union 5 to infinity. And the last one we'll look at is we have f of x equals the absolute value of x, but we are mapping it with this mapping notation. So it says write the equation of the child function. This is moving right 2 and down 1. So we'd have y plus 1 equals the absolute value of x minus 2, or y equals the absolute value of x minus 2 minus 1. If we were to sketch this, again, the best way to sketch this is to write down the parent function, xy table. So we know the parent function has a vertex at 0, 0, so you have -1 and -2. The absolute value of those are 1 and 2, 1 and 2, 1 and 2. So our parent function would have those points. The mapping notation tells us that our child is moving right 2 and down 1. The mapping notation says for every x value, you subtract or you add 2. So you take each x value, -2 plus 2 is 0. -1 plus 2 is going to be 1. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. And then for each y value, you're subtracting 1. 2 minus 1 is 1. 1 minus 1 is 0. 0 minus 1 is negative 1. 1 minus 1 is 0. 2 minus 1 is 1. And so you have your new points for your child function. And so you plot those: 0, 1, 1, 0, 2, negative 1, 3, 0, 4, 1. And you have your new graph. So go ahead, work on the homework, and come back to class with any questions.